today's video, we're going to continue our exploration of the relationships inside of triangles, and we're going to develop what we call our triangle inequalities. So we've already determined that three angles make a triangle if they add up to 180 degrees, but I'd like to determine a similar relationship with the side lengths. What sides or what different lengths can we make a triangle out of? So here we have three examples. We'll start with the first one, 6, 3, 2. So what I'll do is I'm going to start with side length 6, use it as the base of my triangle. And then I'll attach the 3 and the 2 to either end. Unfortunately, we see that we're having trouble making the 3 and the 2 meet. They're just too far away. What if I change it up? What if I use one of the smaller sides as the base? Now, the 6 is too long. Now, I can't get those to match because the 6 is over. I can get them to match up, but that doesn't count as a triangle because we have some extra overhang. So 6, 3, and 2 can't make a triangle. 6 is just too big. What if I change the 3 to a 5? Now let's try 6, 5, and 2. So I'll use the 6 as the base, I'll throw the 5 on one end, the 2 on the other, and just like magic, they line up. But easy enough, I can have a triangle with 6, 5, and 2. So if 6 was too big, if the other sides were 3 and 2, 6 was just fine if the other sides were 5 and 2. What if the other sides are 3 and 3? Now, as I try to use 6 as a base, throw 3 on either end, the only place I can get them to actually touch is on the side that's 6 units long. So 6, 3, 3 doesn't make a triangle, it makes a line segment. So if 6 was too big, if the two sides were 3 and 2, 6 was just right if the sides were 5 and 2, 3 and 3 were just a hair too small to actually make a triangle out of. This is what we call our triangle inequality theorem. What the triangle inequality theorem says is that the sum of any two sides of a triangle have to be greater than the third. So here we have triangle ABC. That means that AB and BC have to add up to be greater than AC. And this is true for any pair of sides. AB and AC have to add up to be bigger than BC, and BC and AC have to add up to be greater than AB. Now we can use this to tell if any three sides can actually make a triangle by adding up the two smallest and checking if it's bigger than the third. So if we look at our first example, 4, 8, and 10, I know 8 and 10 are going to be bigger than 4, and I know 10 and 4 are going to be bigger than 8. What's important though is that 4 plus 8 is bigger than 10. So 4 plus 8 is 12, and 12 is greater than 10. That means I can make a triangle out of 4, 8, and 10. But now let's look at the second example. The second example, we have side lengths 7, 9, and 18. Now, 9 and 18 are greater than 7, and 7 and 18 are greater than 9. The important one is to check the two smallest. 7 plus 9 is 16, which is not greater than 18. Unfortunately, I cannot make a triangle with sides 7, 9, and 18. We're going to run into the same problem we did with the 6, the 3, and the 2. We can also use this idea to determine what the third side of a triangle might be. So here we have a triangle that has a side length of 21 and a side length of 14. I won't be able to figure out exactly what my missing side is, but I can at least tell what it could be, what its range of values is. I know 21 plus 14 has to be greater than the third side, and I know that x plus 14 has to be greater than 21. So that first inequality tells me that 35 is the biggest my side can be. And the second inequality tells me that 7 is the smallest that side could be. So I don't know exactly what it is, but I know it's somewhere between 7 and 35. And finally, I'd like to explore how the segments and the angles inside of a triangle are related. It turns out that if any two sides of a triangle are not congruent, the angle that is opposite the largest side is bigger than the angle opposite the smaller side. So in this triangle ABC, what that says is, if segment AC is greater than segment BC, then the angle that's opposite AC, angle B, has to be greater than the angle that's opposite BC, angle A. And the reverse is also true. If any two angles are not congruent, then the biggest angle is opposite the biggest side. So if angle C is bigger than angle B, then AB, which is across from angle C, is bigger than AC, which is across from angle B. We can use this to arrange the sides in a triangle based on the angles, and arrange the angles based on the sides. So here we have a triangle ABC, where I know how long each side is, but I want to order the angles from biggest to smallest. I won't necessarily know how big each angle is, but I can still at least tell you which one is the smallest and which one's the biggest. Angle C is across from our shortest side AB. So that means angle C has to be the smallest angle. Angle A is across from the next smallest side, BC, so angle A has to be the next biggest angle. And angle B is across from the biggest side, AC, so angle B has to be the largest angle in that triangle. So from least to greatest, those angles are angle C, angle A, and angle B. And we can do something similar with the sides in a triangle. BC is across from the smallest angle, angle A, so BC has to be the shortest side. AB is across from the next biggest angle, angle C, so AB has to be the next biggest side. And finally, AC is across from our biggest angle, angle B, so segment AC has to be the largest side of the triangle. So from smallest to largest, the sides are BC, AB, AC. Thanks for watching.